The next speaker is Giovanni Marchisi from DigitalGlobe, USA.
Не знаю. Он сейчас что-то листал.
Спасибо. Good afternoon, dear colleagues. It's a great honor to be here for the second Oracles conference, for me at least. I am from DigitalGlobe and I lead the effort on image information mining. Image information mining has to do with converting raw imagery into useful information layers. I will show results of original research which is done by DigitalGlobe, by my team at DigitalGlobe, sometimes in cooperation with universities and government labs. Our ambition here is to create a digital living inventory of everything on the surface of the planet. And our core competency are in computer vision, machine learning, crowdsourcing, and data fusion. These are the three pillars on which we're trying to build our solutions. Now, automation is important from the point of view of being able to process very large amount of imageries and building solutions that are scalable to a regional, country, or even continental level. Validation is important. You need the human in the loop to provide the level of accuracy that makes this data layer useful, and that's where crowdsourcing comes in. And last but not least, context is important by actually fusing the information in optical imagery, which is the type of data we typically process, with other ancillary sources of information like synthetic aperture radar or ancillary data such as news feeds and social media. You can provide intelligent context to the imagery. We operate a constellation of 5 satellites, Iconos, QuickBird, WorldView 1, WorldView 2, and GeoEye. They all have sub-meter resolution, and they also have an accuracy which goes as low as below 3.5 meters in the case of WorldView 2. WorldView 2 is a unique satellite because it's the only satellite in its class that has a native resolution of 1.8 meters, 8-band multispectral sensor. So the only satellite in its class which has 8 bands. And I will tell you more about the applications that can be built on this capability. The collection capacity of very high resolution sensors has increased 12-fold in the past 5 years. Today we can collect up to 3 million square kilometers per day. That means that we have the ability to cover the landmass of the Earth at least 7 times per year or every 50 days. Also, 33% of the imagery in archives is less than 1 year old. And add to this that we have the largest very high-resolution commercial image library in the world, with over 4 billion square kilometers being covered. Now, if we utilize our collection capacity intelligently and we focus on the landmass of the planet alone, we already are in a position where we can image every single settlement on the surface of the planet and every communication corridor at least twice a month. And when it comes to crops, we can actually monitor every month. And these at the resolution of 50 centimeter panchromatic, 2 meter multispectral. So this actually opens great opportunities for the research applications that you will see now, because most of them are related to agricultural or forest monitoring, or to monitoring of urban development and urban sprawl. This slide gives an overview of the substantial effort in image information extraction that is going on in my group. When I found out that my presentation is only 20 minutes long, I had to cut it, so I cannot cover all these topics. And I will try to show a lot of information, but the reason I'm showing this slide is that it shows the philosophy of our approach. So as I said, most of what you're seeing today is innovative research in computational methods, and it follows a logical approach. We start with very simple pixel-based semantic models, which leverage spectral and textural properties of the image. Then we move on to more complex models, which look at morphology. That's another property of imagery which is seldom exploited. And then we have more complex semantic models that are able to recognize in the objects from an aggregation of pixels or from an aggregation of shapes. And then on top of this, we have even more complex models that are able to recognize relationships between objects. So I will only cover a few of these topics. Primarily in the area of land use land cover classification, extraction of building footprints, and object recognition, tracking of activity in times, and some pattern recognition. Okay, I will start with land use land cover, and we have some unique strengths here. First of all, we have a proprietary technique for atmospheric compensation, and it is very important actually, because being able to reproduce and deliver a reliable spectral signature is important to all kinds of image information extraction. Shown here in black are the spectral signatures of two end members, grass and sand, as seen by Worldview 2, and shown in blue is what the top of the atmospheric correction would give you today using commercial off-the-shelf tools. Now, we have spent almost 2 years developing a technique that produces the results in red. In other words, we are able to deliver true surface reflectance, which is within 4% of what a ground spectrometer would measure. So this is actually a very important component of our superior approach to land use and cover classification. Also, we have a unique sensor in Worldview 2 in that we can actually record 8 multispectral bands. And also we try to, when it comes to analysis in the area of forestry and agriculture, something which is very important is to be able to work with time series of images, because then you capture the phenology and the growth patterns of different species. And this is especially important because in Worldview 2 we have 2 unique spectral bands, the yellow band and the red edge, which are very sensitive to different evolution patterns in crops. The position of the red edge has to do to the limit where plants stop absorbing radiation for the purpose of photosynthesis, and the yellow band is strategically positioned to detect the replacement of chlorophyll by carotenoids. So by putting all this together, we're able to do superior land use and cover classification analysis. So there is a large strip, it's about 3,500 square kilometers taking over Northern California. It has hundreds of agricultural fields. It has the entire city of San Francisco, Oakland, and Modesto. And we actually are able to extract textural features from the high resolution 50 centimeter panchromatic band. Shown here are examples of grayscale co-occurrences and Gabor directional features. We actually compute those at multiple scales. And then when it comes to spectral attributes, we can create 28 possible band ratios using the 8 bands in Worldview 2. So we discover some unique combinations that are very important for material differentiation and for vegetation studies. We also have models that allow us to study and model the spatial dependencies of spectral signatures. And I'll show you you actually a fantastic results here that we obtained through the time series of imagery over Northern California. There are two crops here which look the same using in the visible light RGB, and by using a single band, which is the red edge, we are able to see the difference between those two crops quite dramatically. So what I'm plotting here is the average surface reflectance for the red edge band for those two crops. It means that we have actually caught one of the crops during a critical phase of transition in the growth. At the end of all these, we're able to deliver very accurate 2-meter resolution land use uncover class. This has 18 classes, and we measured the accuracy of these at 85% or more. The level of details allows 3D discrimination. Very quickly, I will show an example from Russia, where we are doing forest classification. This is from the Sochi region, and we're able to easily classify conifers versus deciduous trees versus grass. Another example from Mexico that shows the ability to do individual tree-crown segmentation, recognizing that there are actually in area number 1, there are some very large trees. In area number 3, actually, we have a very large number of small trees of the same species. This is very important because the study I showed before had to do with accurate determination. By actually being able to do this type of more precise classification by individual tree crowns, you can do volumetric studies. And here we are able to detect potential pine beetle infestation, and these are planted orchards. So enough for land use uncover classification. I'll move to a more exciting topic. So this actually has to do with a very innovative technique that we call the HUG. HUG is an acronym that we invented. It stands for High Resolution Urban Globe. This is an adaptation of the global human settlement layer. It relies on a new revolutionary technique for differential morphological decomposition that was actually invented at the Joint Research Center of the European Commission. We hired 2 of the inventors, and they're actually working with us adapting this technique to our sensors. So this actually has to do with exploiting another property of images, which is the occurrence of regular geometric shapes, especially when you're trying to track man-made objects. Behind all these is the ability to represent information imagery, in the imagery using hierarchical representation known as max and min trees. So max trees captures the hierarchical contrast between bright structures against a dark background. Min trees do exactly the opposite, but they actually provide an ideal framework within which you can do shape filtering based on shape property very, very rapidly. So I can actually construct this differential morphological profile, organize it using this hierarchical structure, and then do very, very rapid filtering of shapes by using a moment of inertias, perimeters, perimeter complexity, and other shape restrictions. So I could actually customize this technique to detect rectangles, circles, polygons of all kinds. Now, the most obvious application is in the automatic detection of man-made structures or building footprints. And we are in the process of testing this process for scalability in many parts of the world. So there are 2 steps. The first one consists in creating a probability map, and within the probability region, you perform the fast morphological decomposition. And what I'm showing here is an RGB rendering of 3 of the spatial properties, of the morphological properties. So there is an RGB composite that encodes area and moment of inertia and eccentricity. So we've done tests in several parts of the world. There is a building extraction from Sana'a, Yemen. Again, the color actually tried to group together buildings of the same shape, of the same properties. There is Thessalonica, Greece. And this is at a 2-meter resolution scale. We can operate on both panchromatic imagery and multispectral imagery. This is from the Philippines. This is from Australia. And this is a large-scale experiment where we did the entire country of Japan, which is about 400,000 square kilometers, in 3 hours using 200 CPUs. So this gives you an idea of the speed and scalability of this technique. And at 2-meter resolutions, we actually produce a map of all the buildings in Japan at 2 meters resolution, and we compared against what is on Google Earth or OpenStreetMap. We found buildings in many localities which are of peripheral interest. So these are some examples of the level of detail that we are able to automatically extract. And we are also very active in many parts of Africa where the mapping of of dwellings in general is very poor. So this is an example from the South Sudan. As you probably know, we're involved with George Clooney with the satellite Sentinel project between South Sudan and Darfur, where there's been war. And we're actually mapping the location of all the buildings. We are actually doing the building extraction over very large areas. We're delivering these in vector form, and what we deliver as the centroid of the building, the area occupied by the building with the building classification code and the measure of uncertainty. And also we are able to produce much more accurate population density estimates. There is an example of over the city of Kabul in Afghanistan. On the left you see the Langscan kilometric population density estimate. On the right is the population density estimates that we obtained by using our sensors. This is actually much higher resolution, 100 meter cells, and this actually is taken from an orthomosaic of 8 WorldView 2 strips. An example from Russia in the field of precision agriculture that combines the land use and cover classification with the ability to extract shapes. So two strips, one from the Moscow district, the other one further south from the Krasnodar district, where the crops are very different. And what we're doing here is two things. So that's the input strip. There is a land cover classification that groups together crops of the same type, by the same color. And there's actually a segmentation of the field boundaries. Actually, the first step in any agricultural monitoring campaign is extracting the field boundaries. Once you have a database of field boundaries, then you can compute agricultural indices. So we actually have automated this process. It's very efficient. These are the same results from the Krasnodar region. There is the land use and cover classification showing the different crop types. There is the automatic field boundary segmentation. The color code scheme here is designed to highlight the difference between two adjacent fields. But this is very fast. In theory, excluding I/O, we can actually extract the field boundaries for 1 million square kilometers in 10 minutes on a single 128 CPU rack. The land use and cover is a bit slower. 2 days actually for the same area. These are some examples of automatically extracted field boundaries, and we found that they are good enough for agricultural monitoring campaigns. A few words about modeling patterns of objects, and we have several efforts in-house. They're using graph-based knowledge discovery, region co-occurrences, hierarchical clustering. I'll focus on color shape histograms. This essentially takes the output of the morphological decomposition, and then it tries to cluster shapes according to their properties. So here is a scatter plot that shows the area, the first moment of inertia, the second moment of inertia, the eccentricity, and the angle. By using these properties, we can do some very sophisticated land use and cover classification. We can actually model the patterns of trees in orchards and do the type of classification that would not otherwise be possible if you were to model just the textural and spectral properties of images. So this is very scalable. We can process 33,000 square kilometers per hour on a single CPU. And by the way, there is the standard for all the benchmarks I'm quoting. They are all Intel 7 2.4 gigahertz processors. By the same technique, we can actually recognize irregular building arrangements of buildings. So this is actually selective SLAM detection from the city of Rio de Janeiro. This is a WorldView 2 image covering 160 square kilometers. We are selectively extracting only the building arrangements that seems to be irregular and match the pattern of a slum or favela. as it is known in Portuguese. So this is actually what it looks like from Earth in the World View 2 image, heat map, and selective building extraction. Another one, and you will notice that there is a legitimate residential development to the north, a legitimate industrial development to the south. The algorithm recognizes only the area which is irregular. And we discovered a new favela by using this technique. I wish I could spend more time on this. I am showing a lot of results, just an idea of what we are doing in the area of object detection. We are taking a very successful example in computer vision, which is face recognition. The approach there is known as Viola Jones. They use essentially cascades of weak classifiers combined with aggressive feature selection via ADA boost. And we have actually taken a very similar approach, except that what they use is like features computed from wavelets, and that the stack of input vectors is huge, up to 260,000. What we have done, we have replaced these features, guess with what? We have replaced these with the more sophisticated morphological decomposition, which is more suitable for our two-dimensional high-resolution images. And this is an example of object detection. The simplest type of object is cars here, and what we are doing here, we are monitoring a Hyundai manufacturing plan. We are actually able to distinguish between the cars that belong to the employees. The cars which are being produced are parked there, then there is a railway here, and the cars are moved here before to shipping. And there is a movie. We are actually revisiting the plan every few days, and we are actually counting how many employees are working and what type of vehicles, how many vehicles are being produced and shipped. So it actually takes longer to show the movie than to count the cars, but when I'm finished, I would have gone through 250,000 or 250,000 cars automatically extracted. Last example has to do with crowdsourcing. We use crowdsourcing extensively in monitoring campaigns. This is actually from the Oklahoma tornado, which happened last May in the United States. Within hours of the tornado, we deployed our imagery, and we trained the crowd how to recognize and label damaged houses, blue tar proofs, and downed trees. And this is actually a result of the crowdsourcing effort. These are images that shows the destruction, and this is actually on a large scale. Within 1 hour, we had 15,000 tags clearly delineating the extent of the damage. Within minutes, actually, from acquiring the imagery, we could produce a machine learning output using land use and cover classification that could guide the crowdsourcing effort. I actually stop here, but there is something I really want to show very quickly, if I can get out here. So this is an image of downtown Moscow. What we have done, actually, we have extracted all the cars in downtown Moscow in about 10 seconds. So automatically extracted cars, and this is actually a modification of the prior algorithms. These cars are actually moving. We're able actually to detect them automatically with an accuracy of 95%. So we can do this every week for every major city in the world. Okay, thank you for your attention.
Thank you, Giovanni. It's quite interesting presentation. I think that your results will be very useful for government of Moscow to fight against bad traffic in Moscow.
Thank you.
To predict traffic problems. Вопросы, пожалуйста. Пожалуйста.
Would there be questions for the speaker? I don't have a question, but more like a congratulation. I would like to congratulate you because one of your satellites from your constellation has a birthday, if I'm not mistaken.
So is it? It cannot be WorldView 2. It's not GeoEye. Is it WorldView 1 or which one? Iconos, okay. Well,
Iconos.
I am younger than Iconos.
Еще вопрос.
Would there be other questions? Rosenfork, tell us, please, what is the depth of detailization when you identify cluster on forest vegetation? The depth of detailization.
Detail.
Yes.
In some cases, we can go to level 3 Anderson classification, especially if we work in the time dimension. So sometimes we can resolve individual 3 species only if we work in the time dimension. So level 3 Anderson level classification. Does it answer your question? I can talk more, yes. We can talk more afterwards, yes.
Спасибо, еще вопрос.
Oleg Gomuzov, Institute of Exact Tools. Do you have plans to implement these things through a commercially distributed software, like the ones that you are going to sell? Or maybe we can have access to your software through different web services?
Exactly. I am thinking of doing 2 things, either to extract these layers in-house, and actually we have a plan. We could actually process the daily take and do this type of extraction routinely every day for the 3 million square kilometers we extract every day. We could actually automatically extract all these layers and sell them, or we could actually make the tools available via web services. I'm in favor actually of making these tools available to customers and partners like you through web services. Yes, that's the idea.
Еще вопросы?
More questions?
Thank you.
И сейчас